Okay, now let's focus on the first part, adversarial purification. Let's try purify the upcoming test data. Yeah, we can look at this image. It's from a previous intro video. Okay, we want to purify, it happens in the input phase. We want to purify any data, upcoming data to remove possible adversarial noise. So the main research trajectory here is to use powerful generative models to purify adversarial examples. The high-level idea is to use pre-trained generative model on nature example to reconstruct the adversarial example into samples that are close to nature example. And the intuition is that a generative model reconstructs samples based on its learned knowledge because it's trained on the nature example. So for example, it's a manifold of nature examples. Thus, a pre-trained generative model on nature examples will align any examples to the manifold of nature examples during the reconstruction. So here we can look at the general pipeline for adversarial purification for the current method. The black curve means the manifold of nature examples in a 2D sample space, okay? And the green dots means the nature example. We can say for green dots, it's actually near to this manifold, okay? But for the adversarial data, the red cross, adversarial data is far away from this manifold. So in adversarial purification, nature idea here is we want to just make adversarial data close to this manifold, okay? Here is a very representative work in adversarial purification. It's called magnet. The main idea here is to use the reconstruct power of autoencoder to purify or reform adversarial examples. But the limitation is that the autoencoder is not strong enough, okay? The autoencoder is just a very basic generative model, it's not strong enough, and it cannot purify examples that are far away from manifold of nature examples. So how to solve this limitation? In this paper, the authors just use a detector, okay, to filter out hard to purify adversarial example first, and then use autoencoder to purify remaining adversarial examples, okay? And the rationale here is that any adversarial examples that cannot be detected by detector must be close to manifold. So we can't just use autoencoder to purify them. Okay. Yeah, this is a pipeline for the magnet. We can say for the example for detect, if an adversary just we throw it away. If no, we want to use autoencoder to reform this data to X prime and feed it X prime to target classifier, right? Get the final class labels. Okay. And here is question, can we purify adversarial examples without filtering out these hard purified ones? The answer is yes. The nature idea is to use a stronger generative model. Okay. And later on in 2018, researchers proposed another work based on generative model, okay, based on generative model. The solution is to use a pre-trained GAN model to reconstruct adversarial examples, okay. Yeah, we can look at the main pipeline here. So here we will give some seed to GAN, okay, some seeds, okay. For different seed, we will get different generalization. It's just image. GFZ is one image, okay. And then we can also have the input image. You can consider it's an upcoming image, okay. And we can find the best state, Z, okay, we call it Z star, such that it will minimize the difference between JZ and the given image X. And then we give this Z star to generator, and we will generate another X, okay, we call it X hat. So X hat is our purified example. And that's how we use the power of a pre-trained GAN to help us purify or reform an input image X. Okay, finally we give this X hat to classifier, get Y hat is a prediction label. Okay. And almost the same year, and research also want to use a pixel CNN to reconstruct other examples. Here, pixel CNN is a generative model with a trajectable likelihood, especially designed for images. The model defines the joint distribution over all pixels by factorizing it into productive conditional distributions. Yeah, it's more like probability model. And next work in this field is relatively near. It happens in 2021. In this work, the motivation is that if we treat adversary purification as a process of denoising adversary attacks, why not try a general model that is designed to denoise the perturbed samples, right? So it's actually linked to the score-based method or called diffusion model. The solution is to use a pre-trained general model with denoising score matching, okay? And it means a score network, which is particularly good at denoising perturbed image with noise. So this is actually the breakthrough idea. The idea, it means that now we have some images, okay? It might contain adversary noise. So how could we just get rid of this noise? We can first inject some noise, okay? For example, we inject Gaussian noise. And after we inject Gaussian noise, we will let the effect of adversary noise weaker and weaker, okay? And then we just use a pre-trained score network to remove the noise from image, right? So it's like we know adversary is just a noise, small noise. So we can add more noise to the image and try to let adversary noise have very light effect. And then we just use the score network to remove the Gaussian noise we injected and get the final images. Okay, yeah, that's a very important idea in this field. And based on this idea, we have a nature idea, okay, after this paper. Can we use a stronger denoise general models? For example, diffusion models? The answer is yes, and it just makes this field thriving, okay. So the next work, DeepView, published in SML 2022. The solution is to use a pre-trained diffusion model to denoise adversary examples. And the rationale here is to inject Gaussian noise to adversary examples, makes the distribution of adversary example approach a Gaussian distribution. Ideally, the distribution of noise injected adversary examples should approach the distribution of noise injected nature examples, right? Because it's like we're continuing A to add the Gaussian noise to images. Finally, this image might look at nature image plus Gaussian noise. And then we just use the diffusion model to remove this noise. Okay, yeah. Yeah, however, in this kind of method, the t is very important, okay? If the t is very small, then distribution of noise injected adversary examples cannot align well with the distribution of noise injected nature examples, which means the adversary noise cannot be fully removed. If t is too large, then the image will become too noisy, right? Which will lose semantic information without the guidance of the original semantic information. The purified image may have a different semantic meaning. And then researchers try to understand the diffusion model for adversary robustness, right? Because they have some like the problem about T, okay? And in this method, it's called dense PU. They provide a proof, like when data density of nature samples is sufficiently high, the conditional density of the purified example will also be high. This means that samples drawn from this conditional distribution have a high probability of recovering the original semantic meaning. So how to use this theoretical result? Researchers consider to purify input multi-times, okay, and get multiple purified samples. Then feed them into classifier and use majority voting to select the final prediction. It's a very nature idea based on their theoretical result. It's published in Clear 2023. So here's the pipeline. We give input to the off-the-shelf diffusion model, and we got a conditional distribution. And then we do it again and again, right? We sample a lot. We can say here it's just the peak, and here it's dog, okay? Yeah. even the dog will be obtained based on the diffusion based the adversarial purification. But after voting, we can say, okay, the prediction should be the pig instead of dog, okay, because it's a majority is a picture of pigs, it's pig, okay. Okay,